Hello everyone to the 6th edition of the Quantum AI monthly series. Today we have very nice speakers and experts from all over the world, from Egypt, also Tunisia, the Netherlands and France and Europe in general. And today features the quantum education and also how to promote quantum education and enhance quantum education in general. First of all, we have about 6 presentations. We are going to start with giving a bit of update about the hackathon. We have now a dry run hackathon to prepare participants for September's hackathon in Alexandria. And then we are going to have a presentation by Dr. Ahmed Younes about the QEgypt mission and also quantum education in Egypt and work in building quantum futures. Then we will have another talk by Dr. Murad Telmini about quantum science and technology in Tunisia. This will be followed by a talk from Alain Chancey about quantum education and research featuring sample-based quantum diagonalization. Then Dr. Mohammed Amin Mouradi is going to present how to stimulate and enhance quantum education. The last presentation will be fun. It will be by Sejord Weichers. Do I pronounce the name correctly, Sejord, or can you correct it for me?
It's good enough.
I see. Yeah, I didn't pronounce it much, so this is probably I will need to practice it more. But it's a very nice name anyway.
Thanks.
And that is gonna be about quantum meets video games inspiring the next generation. So first, a bit of update about Alexandria Hackathon. We are gonna now present Youssef Eldakar is the head of International School of Information at Bibliotheca Alexandrina. So Mr. Youssef also works to provide support to research through the technologies of parallel computing, big data, natural language processing, and visualization. He's also worked in HPC, high performance computing, was assigned in 2013 to lead Bibliotheca Alexandrina HPC service, providing a platform for high performance computing to researchers in Egypt and at times regionally through European collaboration. He's also have done several projects like web archiving, which is a very nice and also foundational project at Bibliotheca Alexandrina, and also he's represented Bibliotheca Alexandrina as an international Internet Preservation Consortium since 2011, and also is a member of the steering committee since 2018, and the lead of the tool development portfolio since 2021, and served as consortium chair in 2023. Also contributed to the book digitization during the initial phase of the effort at Bibliotheca Alexandrina and started a project LinkGate for large-scale temporal graph visualization, and also several other projects like project NoAdmin for HPC account automation, leads to Bibliotheca Alexandrina internship program for students of computing, and also has been profiled in Marcos Who is Who in Science and Engineering. Okay, Engineer Youssef, please go ahead.
Thank you very much, dear Dr. Taha, for the introduction and as well for all the efforts you have been leading to build the community and prepare us for the hackathon to come in September. And also very special thanks to all our speakers this time and all other editions of the multi-series. We're very honored to have you. Thank you very much for joining us and contributing your valuable time to this series. We are very happy that we are coming closer to the hackathon, especially that the past couple of days we had the dry run hackathon hosted online. It was a very encouraging thing, a very positive thing to witness and see the interest, the motivation, the effort, the development, the learning, and the work on the projects, the ideas, which makes us look even further to our hackathon in September. The plans are now much more clear. We look forward to it being a very fruitful event for everyone. And we're also very happy to see all the preparation that's happening, even at different universities, especially, for example, I know Professor Ahmed Younes has an excellent summer program for quantum computing education that he's offering to students at the university, the Alamein International University, and any other efforts elsewhere. So I'm sure everyone is looking forward to the rest of the talks. So I'll leave more time to that, and we're happy to answer any questions on the groups, and we look forward to seeing you and continuing the journey together. Thank you.
Thanks, Mr. Youssef. So first, a bit of introduction. So I'm also currently general manager of a startup called MolKet SaaS, based in Paris, in France, and also held an academic position as lecturer and researcher at Amsterdam University of Applied Sciences, working in quantum information and computing. Here I would like to start with thanking the special team of the Dry Run Hackathon. Of course, that was a last-minute slide organization, so this is why the pictures are not aligned, but all the thanks to them, and we are looking forward to work on a very nice hackathon in September, and very nice collaboration as well, bringing all the students from all over the world, from Egypt, and the mentors from all over the world. Now we are going to start with a presentation from Dr. Ahmed Younes about QEgypt mission, quantum education in Egypt, and also work in building quantum futures. Also, Dr. Ahmed, as Youssef Eldakar has mentioned earlier, he's organizing a summer training, a national summer training in quantum computing for all undergraduate students, allowing them to advance their careers and also understand new technologies and be ready to be a future workforce. So if you are an undergrad, feel free to know more about this opportunity so you can participate if you are not participating at the moment. So Dr. Ahmed Younes now is a professor of quantum computing at Alamein International University. He's a representative of the Arab states in the International Year of Quantum Sciences and Technology, IYQ 2025, steering committee endorsed by UNESCO. He's the founder and the leader of Alexandria Quantum Computing Group. He's also the manager of the Center of Excellence for Quantum Computers at Alexandria University. He's working as coordinator of the Professional Master in Quantum Computing and Quantum Informatics. He's also coordinator of QEgypt and the representative of Egypt in the World Quantum Day. He was a former Vice Dean of Education and Student Affairs at Faculty of Science, Alexandria University. He was a former manager of the International Scientific Publishing Center at Alexandria University, and held other academic positions like academic supervisor at the Faculty of Computers and Data Science in Alexandria University, former honorary research fellow at School of Computer Science, University of Birmingham, United Kingdom. He also got a PhD from the same university in quantum algorithms and the quantum circuits in 2004. Okay, welcome, Dr. Ahmed. Please, the floor is yours.
Thanks, Dr. Taha, and thanks, Engineer Youssef, for the invitation. It's always glad to be with you in this monthly meeting. Can you hear me well? My voice clear?
Yes.
Okay, I'll try to share my screen. So can you see my screen now?
Yes.
Okay. As far as I understand from Dr. Taha, this monthly meeting is this time is about education, what we have been done or doing in Egypt in the education of quantum computing. So I will just quickly give an overview of what we are doing. We are doing all these efforts through Alexandria Quantum Computing Group, which has been established as a group since 2016. It started earlier as PhD and master students but we are actually now some kind of community has some commitment. We feel that we have some commitment in research, in education, in innovation, in collaboration and community service. Today, I'm going to focus on the education and the community service related to education, what we are doing in Alexandria Quantum Computing Group. These are our members. We have quite a good number in faculty members, PhD students, master students, and professional master students. And I can see that many of these names are in the list. Just Dr. Taha showed that helped in the dry startup of the hackathon. I'm glad they are doing very good activity and they are useful to the community. The group is not only affiliated to Alexandria University. The group has members in quite number of universities in Egypt. These are the affiliations of some of the members. In terms of research, we are doing research in different topics such as quantum algorithms and amplitude amplification techniques, quantum machine learning, quantum circuit sciences and optimization of quantum circuits. We are working in quite some topics. They are all related to computer science. We all have backgrounds of computer science. Quantum computing is not only computer science. Quantum computing, as we are going to see, covers many other topics. Before I start to show what we are doing in terms of the education, I'd like to show, because when we try to build an educational program or educate people, we have to understand what are the activities, what are the main topics in this field, to build as much as we can a comprehensive program that can serve the community in this field. So for quantum computing, companies are specialized either in quantum sensing, quantum communication and cryptography, quantum hardware, quantum algorithms, and some facilitating technologies. We have to examine the market. We have to understand how the market works to be able to build this educational program in a correct way. So these statistics shows the activities of the companies in quantum science and technology field. We can see that much of the work has been done in quantum software and in quantum hardware. Some other topics are very important, but mainly the activities is in quantum software and in quantum hardware. If we check the companies in the region, this is, I don't like this image actually, because in Africa we don't have much number of companies established in Africa. We are working hard to make this number increases. That's why we decided to start these educational programs in Egypt 3 or 4 years ago. This statistics shows the demand of the market per year. This comes from a paper published in Photonics View in 2020. It shows the increase in the number of jobs by years. So we are expecting this increase very soon. And actually, I believe this paper is old now. 2020 was 5 years ago. I believe after IYQ 2025, if we did the same study again, actually this curve will be different. I think the increase in the number of jobs will be much higher. So we have to be ready for this. We have to prepare the students, the graduates for these jobs. And we have to understand the ecosystem. Actually, the ecosystem consists of 4 main pillars: the academia, the government, the industry, and the general public. So we are working from the academia side. Dr. Taha and Bibliotheca Alexandrina, Engineer Youssef, are working from the general public. They are approaching the general public in a very, very good way. We are trying both. We are trying to help the industry, and we have some effort with the government. The government always takes decision in a different way. We are working hard to get their attention and get their interest in quantum technology. So these are the technical skills we need in the quantum industry. They cover many aspects, many topics. But we can help in as a computer science. We can help in algorithms and computer science. We can help in coding skills. We can help in data analysis. Some other skills should come from different disciplines, such as engineering or physics or mathematics or others background. This is this image is shows that we need educational program as soon as possible, because actually currently the market 61% work in the market by the PhD holders in quantum science and technology. Actually, no ecosystem, no market can be established in a correct way with this percent of PhD holders. PhD holders should be smaller and bachelor workers should be higher. So we need educational program or even master students. So this curve or this chart should be corrected through the educational program by offering enough educational program to cover the need of the market. This is the effort done worldwide in terms of funding, global funding in quantum science and technology. Also, I don't like this image because it shows that actually Africa don't offer enough fund for this, and this actually should be. We have to work on this image somehow. So before we design educational program, we have to decide what is the strategy, what is the framework to design this educational program. So generally we have four choices. We have to choose which framework to work on. The classical one, the first one is a disciplinary approach, where students study only a single discipline during their study. So they either study physics or computer science or mathematics or chemistry and so on. But this approach is not suitable actually for quantum science and technology and the quantum computing. Most of the programs I saw on other universities, they are working in the multidisciplinary approach. Multidisciplinary approach is they gives the student a dose in physics, quantum physics, or for example, and computer science and mathematics, but they do not overlap in the teaching, in the coursing. And I believe this is not the correct approach to build educational program, because quantum computing has its own uniqueness. It is new science. So we have to design the educational program either in the interdisciplinary approach or the transdisciplinary approach. What is the difference? The interdisciplinary approach, for example, the student should study some courses in computer science, some courses in physics, and some courses where the difference between physics and computer science, or even in mathematics, they dissolve. So this course, you cannot decide if this course is physics or this course in computer science. This course is specialized in quantum computing. So it covers it. The differences between these topics should be dissolved in these new courses. I hope one day we can reach to that transdisciplinary strategy where we cannot see the boundaries between all these topics in the educational program. So in Alexandria University and in Alamein International University, we decided to go in the interdisciplinary approach, and we are hoping we can go to the transdisciplinary approach when the market or the environment is mature enough. That's why we started designing courses since 2005 with a PhD level course in Alexandria University, in Faculty of Science, Alexandria University. In 2007, we started a master level course in 2007. We start to encourage the undergraduate students to do their graduation project starting from 2014. After we have enough teaching assistant and the research assistant graduated from the master and the PhD level, so they start supervising the students in their graduation projects. We do other activities, but this in red shows activities specialized in the education. In 2021, we start undergrad course, complete undergrad course in the course for the fourth level students. In 2021, also we joined global initiatives such as QEgypt. I'm going to talk about it after a couple of minutes. This is also educational programs and for awareness. In 2022, we started a complete program for all students. It's a professional master in quantum computation and quantum informatics. In 2023, we organized summer training for high school students. And this year we are busy with 2025, and we are also organizing a summer training for all undergraduate students in the Egyptian universities, as I'm going to show in a minute. So these are the individual courses we started with in 2005. This is the PhD level course. In 2007, the quantum computer. This is a master level course in Department of Mathematics and Computer Science in Faculty of Science, Alexandria University. In 2021, we started a program for the PECC level in computer science in Alexandria University. And in 2022, we started a course in Faculty of Engineering about quantum computing. We also published a full course for Arab-speaking students. It consists of 15 lectures about quantum computing. It covers all the basics of quantum computing, not very advanced, maybe until Grover quantum search algorithm, but not. Maybe we plan to add more lectures about it. Actually, this channel reached 32,000 views so far. It shows. Actually, I regret that I didn't monetize these videos, but actually it is all free for the students to check. We also organized summer school in 2019 in Faculty of Science. During COVID-19, we organized a winter school. Many students from all the Arab world has joined these schools. This is our Facebook page, and this is our channel on YouTube, consists of many educational videos about quantum computing. During our effort in the education, we encourage the student to do their graduation project in quantum computing. So we have mainly 3 graduation projects. In 2016, a group of students developed a very useful tool as a quantum simulator. We call it Javantum. You can do all the tasks actually on this tool is very useful for the researcher. In 2020, another tool called QKit, and recently we are finishing the last touches in Javantum 2. Maybe it's not for the public yet. It is still beta version. We are trying to debug it to be sure that it is working very well, but it includes many very interesting features, such as export. You can build your quantum circuit here, test it on the simulator, then you export this quantum circuit to Cascade or to Penny Lane or to to search Google quantum computer. We have this part, quantum machine learning. This is very useful feature. We have here algorithm. You can automatically insert most of the quantum algorithm in these days, such as Grover, Schwartz, phase estimation, Bernstein-Vazirani, all these Deutsch-Jose, all these quantum algorithms. You can just click on the name, set the number of qubits, and it is there. This is very useful for the students. We also have this AI assistant feature. You can just type, I want the quantum circuit to do this and this and this, but we still be very careful about AI tools about this. You have to be sure that it works correctly. In 2023, we started a quantum computer program for high school students. It was fruitful, actually. One of the students contributed in a science fair and won the first position. She developed a game to teach the students about the concepts of entanglement and superposition and so on. This is our educational program, the first full educational program offered in Alexandria University. It is a professional master, and these are the courses. And we have to be very careful. We choose these titles, but actually every course in the 4 courses are 2 or 3 courses from the undergrad. So, for example, basics of computer programming, this title is misleading. The content of this course, for example, consisted of 3 courses. Introduction to programming, object-oriented programming, and data structure. So all these courses are separate courses for the undergrad, but we condensed them and make them because we receive students from all backgrounds in this program. They are not necessary to be background computer science or physics or mathematics. Some students are from biology, but they are interested in this field. So we have to prepare them before going to the main courses in quantum computing. So every course in these 4 courses is a combination of 2 or 3 courses from the undergrad. Then we offer these courses specialized in quantum computing, quantum circuit, quantum algorithm, quantum machine learning, and so on. We have quite a long list. These are the teams, our busy teams, full of assignments and homeworks and exams and things like this. And actually, our effort didn't go without a reward, because we received this email very recent. It is a company in Egypt. They are asking for CVs of the students enrolled in this program, because they are starting their activity in quantum computing, and they are asking for the CVs of the students in this program. So we feel that we are in a good path in this program. Also, we are very soon starting in program. This program is not started yet, but it's going to start in Alamein International University. It is a master in computer science and technology, which you can do PhD. And this program consists of some mandatory courses, some elective courses. These are the mandatory courses. And you can check here, we have these elective courses, and we have 2 passes in this program. If your background is computer science and you go in the computer science, so you have to choose one of these courses. If you are going to the hardware or the physical implementation with the physics, you have to choose. So you have to choose one of these. Then you have to choose the rest of the courses from these courses. You can see here we added courses such as quantum sensing, metrology and imaging, quantum optics, quantum physical systems, quantum electronics. So we have part of these courses with computer science background and part of these courses with physics background and physical realization. Also in 2021, we joined the QEgypt. We joined the Q World. Q World, we are representing Q World in Egypt through this QEgypt. So Q World in general is a non-profit organization. Their main goal is to democratize the quantum science and technology through education. I'm sorry for this noise. If you can give me 1 minute. I'll try to make it silent. Sorry. Sorry for this noise. It comes from outside, so I have no option.
No worries.
So, can you see my screen?
Yes.
Oh, thank you.
Yes, we can.
So Q World works for popularization of quantum technology through educational mainly and research recently. We started this research activity recently. So our goal is to have open access and public global ecosystem for quantum technology and quantum software by 2025. We are working on this. Q World has 3 departments: Q Education, Q Research, and Q Cousin. So we are the representative of Q World in Egypt through the QEgypt. This is our page. It's established in 2021. We have approximately 15 members, but actually this number is greater than this now. Actually, Q World offer training in quantum computing through levels. So the first level is the Q Bronze certificate. The second level is the Q Nickel certificate. The third level is the Q Silver certificate. We have another certificate which is Q Cobalt. It is about quantum annealing. We are developing the material and the curricula by time to satisfy the requirement. Actually, Q World certificate are very popular now. Many students trying to get this certificate because it is very good source of information. Recently, we started since 2021. We organized many Q Bronze workshops, but recently in 2024 we organized a Q Bronze. It consists of 519. This was one of the biggest workshops in QEgypt. We also contributed in a workshop through Africa with other 9 countries. All the African students joined this workshop, the Q Prep and the Q Bronze 147. This was for the African students, and it consists of hundreds of students. Actually, it was very good. So by the end of the training, the student gets this diploma about Q Bronze or Q Silver or Q Nickel and so on. Just a couple of months ago in May, we organized Q Bronze 159. It was quite big workshop as well. And we started actually to establish student sub-branches in the university. So we have Q AIU and Q KSU in Alamein International University and Kafr Sheikh University. We have many requests from other universities to establish their Q, because actually the structure of Q World is that Q World, we have Q Cousin in one in each country, and this Q Cousin can establish sub branches under this cousin. So we have many requests. I will not say the names until they are officially joined the network. Also, Q World is organizing Q Inter 2025 right now. It is going. These are our Facebook page and LinkedIn pages if you are interested to follow what we are doing. And this is also the channel. We are currently busy with quantum computing summer training course. We got the number Q course 110 from Q World. Is registered in Q World. This training is offered for all undergraduate students in Egypt. We got 506 students applied for this training. These students are from 64 Egyptian universities. Actually, it shows that there is an interest in quantum computing, and we have to respond because some kind of we are as a specialized person, we are as an expert, so we have some kind of commitment towards the community in this direction. Also, this summer training are working in cooperation with the hackathon organized by Bibliotheca Alexandrina, because this summer training include a project by the end of the training. So we ask them if you can do the project with us, or you can go and contribute to the hackathon. And whatever you got in the hackathon, we will take it as the graduation, the project in this training. I believe Engineer Youssef suddenly find many applications come to his forum, so probably they are from our students. I don't know how many students registered so far, but we need to organize this very soon. I'd like to thank you very much for your attention, and I hope I didn't take much time.
Thanks very much, Dr. Ahmed, for the nice and the comprehensive view about the all wonderful efforts to promote the quantum education and the quantum research in the region, but also in Egypt and in Africa. We have one question in the chat, and then, okay, who's raising his hand? Because, yeah, Greg, please go ahead, because the name is not appearing in my screen. Yeah, Greg, you are muted.
Thanks, Taha, and thank you, Dr. Ahmed Younes. That was quite educational. I'm asking about teaching the general public and what we call in the United States STEM and so on. So my question to you and anyone else in attendance here today is I'm putting together some courses at universities, but be again directed towards younger and non-technical people, non-PhD, as what you were saying, Ahmed, about getting them going. What I'm specifically going to be basing my coursework on is Dr. Bob Cook, the CTO of Quantinium's book, Quantum and Pictures. I've sent a link about it.
Yeah, I know the book very well. Yeah, I know it. Okay. I know Professor Bob personally, by the way. Excellent. I have met them in Dubai. Yeah.
Lucky you. And so what I'm asking all of you, one of the slides that you shared with us, Ahmed, was a lady who had a course for younger people, and anyone else that might be in this presentation, please reach out to me. I'm going to have the courses start in January, and I'd like all of us to dialogue, or I would like to dialogue with any of you that might be interested in trying to develop more of this type of coursework, please.
Yeah, actually, this is one of the main, very important issues we have to discuss in many places about developing these courses, because we have to unify, standardize these courses somehow, because many courses carry the name quantum computing, but when you check the content, they are completely different. So we have to standardize this somehow. So I'd be very glad to discuss this with you or with anyone who have some experience in developing these courses, and we have the curricula and the syllabi, and I'm really glad to have it.
Thank you. That'd be great to discuss it with you. Thank you.
Thank you.
Yeah, thanks, Greg. Thanks, Dr. Ahmed, for the answer. We have another question from Mohammed Fergani. is there a master program in AI in Alamein University? So Muhammad, is it you ask for AI master or is the article of Alamein University? Can you ask your question?
Quantum master. The program is ready. We just wait for the approval from the Supreme Council, and we can start right away. But this needs some processing with the Supreme Council.
Okay, then that's a
Once we
great.
get the approval, we will start. We were planning to start this fall semester. We hope we get the approval before the fall. So just follow the pages of Alamein International University. When it is ready, we will put the announcement.
Yeah,
Okay.
I hope it's going soon, inshallah.
Inshallah.
And another question, it might be also good for the PhD program. What are the current available courses to promote the PhD students who wanted to proceed in quantum computing in Egypt?
Actually, for the PhD program, we don't have PhD in quantum computing. The whole program for quantum computing, we offer quantum computing through the PhD in computer science in Faculty of Science at Alexandria University, and you will get courses in quantum computing during your study, and then you start your research in quantum computing. But I believe the system is not ready yet for a complete PhD program in quantum computing because it is mainly research. So if you get your master, go for the PhD in computer science or in physics and go for your research point in quantum computing. When we reach to enough maturity level, maybe we can start a PhD level in quantum computing.
Okay, yeah, that's really great to hear. So thanks, Dr. Ahmed. There is also a question about the copy of your slides, but I think we are gonna promote a folder.
Yeah, sure. I can send it to Dr. Taha, and Dr. Taha can send it to all the participants.
Okay, thanks, Dr. Ahmed. There is a question from Selim. What program is available for telecom engineering with quantum or electronic engineering graduates or students?
Either the professional master in Alexandria University or the master in computer science, in quantum science and technology in Alamein International University, because these programs are designed to accept students from any background. We will give them the required information from physics, computer science, mathematics as core courses. Then they go to the courses in quantum computing. So any student with any background can join these programs.
Okay, that's great. And please, for Selim, please follow up on the details, also perhaps on WhatsApp or anything, and then you can get the links for those programs. Okay. Thanks, Dr. Ahmed, very much for the nice presentation and the wonderful efforts. And we are looking forward to host you also in Alexandria as well as a jury member and prime speaker in the event, and also to see all of your nice group members and the community.
Thank you very much.
Yeah, thanks. So now we are moving to the next speaker. I'm just sharing my screen. So our next speaker is Dr. Murad Telmini, and he's going to present quantum science and technology in Tunisia. Dr. Murad holds a PhD in atomic physics from University of Paris-Saclay in 1993. He has previous leadership, president of the Tunisian Physical Society between 2005 to 2007. Is a member of the C13 Commission of the International Union for Pure and Applied Physics between 2006 to 2014. He is also the Director General of the National Center for Nuclear Science and Technology between 2010 to 2012, and the Vice Chair of the African Commission on Nuclear Energy between 2011 to 2014. He has current roles, like he is also Professor of Physics at the University of Tunis Al Manar. He's also director of the Research Laboratory on Atomic and Molecular Spectroscopy and Applications, LSAMA. He's also coordinator of the Tunisian Quantum Network, Quantum, and the president of the Tunisian Metrology Association. He's also a visiting professor and researcher at several international universities, including Paris-Saclay, Le Havre in Normandy, University of Sao Paulo, and the University of South Africa, and Bordeaux University in the United States. Has a research focus on quantum physics, like Rydberg states, coherent control with ultra-short lasers, coherent transport of cold atoms, Bose-Einstein condensates, and also quantum computing for molecular applications like the variational quantum eigensolver. Okay, Dr. Murad, the floor is yours.
Thank you, Dr. Taha. So good afternoon to everyone. Thank you, and also I would like to extend my thanks to Dr. Youssef as well. It's a pleasure to be here and to listen to my friend and brother, Dr. Ahmed, and other colleagues. So I was requested to speak a little bit about quantum science and technology in Tunisia. So I prepared some slides I would like to share with you. Okay. Yes, so it's coming. I hope you see it now.
Yes.
Okay, so let's go ahead. Basically, to speak about the QST in Tunisia, there are three pillars actually. So education, research, and outreach. So I will go through these 3 points. Before that, some general information about Tunisia. Maybe not everyone here in the attendance have this information. I think everyone knows where Tunisia is, North Africa. The population is now about 12 million. We have 13 public universities, 250,000 students roughly, 13,000 faculty members, and a few hundreds of big or small teams organized in either research labs or research units. Of course, these numbers stand for all the disciplines. Part of them is dedicated to physics or computer science or electrical engineering or other branches of science which can be related directly to quantum science and technology. So roughly about 0.8% of the GDP is devoted to research and development by the government. The number of researchers per 1,000 active in Tunisia is about 6, with a good gender balance. For PhD studies, so all these numbers once again are for all the disciplines. So about 10,000 students enrolled in PhD programs, and about 1,800 of them were awarded PhD, for instance, in 2022, with some good ranking. As you can see here, according to some specific metrics, and quite strong international collaboration actually with several countries. So regarding the ranking, here I'm showing the ranking, the Shanghai ranking of the African universities, and my university is showing up here at the 12th position. Of course, the leaders in Africa are still the South African universities, and also Egyptian universities which are doing very well. So I can see here among them University of Alexandria and others, and I'm happy about that. Regarding publications also in general, so this map illustrates the publications all over the world. It's a mixture actually of usual maps where the area of each country is now proportional to the number of publications. So of course you have this like distorted map in which you see that most of the publications come, of course, from USA, China, and Europe, and all Africa is shrunk, as you see here, to this very small part, unfortunately. So if you zoom here, you can see still that in addition to South Africa and Egypt, Tunisia also is doing quite well, with in 2020 more than 8,000 publications, which allows us to be very well ranked number of publications per capita in Africa, and also having quite good, not excellent, but still quite good ranking for a few universities in Tunisia. My university, Tunis Al-Manar, the largest one, but other universities like Sfax or Carthage or Monastir, which have like a honorable ranking in different branches, including physical sciences and engineering, where quantum science and technology is the most relevant. So now I'm a physicist, of course. So my colleague, Dr. Ahmed, has a background in computer science. So I will try to give the point of view of physicists in Tunisia. So regarding physics, among the 13 universities I have already mentioned, we have 6 colleges of science, several research centers and institutes, and the research activities actually cover the main branches of physics with a strong international cooperation. And also I would like to emphasize the role of scientific societies and networks like the Tunisian Physical Society, the Tunisian Society of Optics, Quantum Network, Q Tunisia, the branch of Q World, etc. I will come back to this point when speaking specifically about outreach activities. A few words about education, QST education in Tunisia. Here I'm focusing on what I know better in my university, Tunis Al-Manar, but let me say that, of course, basic quantum physics is part of the curricula for decades now, and we have quite large community of people who have this training in quantum, and part of them are continuing to do their research in quantum science and technology. So to be more specific to what we mean nowadays by quantum science and technology, so quantum computing, quantum metrology and sensing, quantum communication. At my university, and more specifically at the Faculty of Science of Tunis, we have introduced in 2019 a new master degree in nanophysics and nanotechnology, and as part of the curriculum of this master degree, in semesters 1, 2, and 3, as you can see here, I put in blue the courses that are directly or more directly related to QST. So this includes advanced quantum mechanics in semester 1, then condensed matter physics, of course, including semiconductors and nano components, cold atoms and quantum gases, which is very popular nowadays in quantum sensing, quantum metrology, but also in quantum computing. So the qubit can be made of of cold atoms and optical lattices. And then in the final semester, you have more specific lectures like quantum information. So this includes quantum communication and the quantum computing, in addition to nanomagnetism and spintronics, superconductivity. So this is also important for the qubits and for the hardware part of the quantum computers. And in addition to quantum metrology, we also use for the quantum computing part of this lecture the IBM Qiskit platform for practicals. So regarding the quantum computing part, we review with the students the main quantum algorithms, going from the very simple Dutch-Jozsa algorithm, Bernstein-Vazirani algorithm, Simon's algorithm, of course, quantum teleportation, then Grover's algorithm, and of course the most impressive algorithm for the students and for people working on quantum algorithm is a Shor algorithm, of course. So for that we need the QFT, the quantum Fourier transform, and the quantum phase estimation. So the students go through these two algorithms, and then they apply they implement on the platform Shor algorithm in the simple textbook case of 4 qubits for 15 equals 3 by 5, as everyone knows here, I guess. So in addition to that, we also we have time to see the QKD and the BB84 algorithm for cryptography. And for some of the students, they are also introduced to the hybrid variational algorithm like variational quantum eigensolver and apply it to quantum systems, like finding the ground state of a quantum system like an atom or a molecule or other thing. I would like also to mention that quantum computing is just starting to be introduced in other curricula like computer science engineering and also electrical engineering in some schools of engineering in Tunisia, but this is just starting. Okay. So now let me move maybe in this presentation, focus more on the research part, as most of our students after doing their master degree go to PhD programs and do the research in the field of quantum science and technology at large. So including, as I said, quantum materials, quantum, so let me just use these bullets to remind them. So theoretical quantum physics, quantum information and quantum computing, condensed matter physics, including the quantum dots, quantum materials, including topological materials. Also the atomic and molecular physics, including lasers and photonic and optics, etc. So we have a quite active community in these fields. I'm going to mention some of them just to give you a flavor. Of course, as requested by one of the attendees from Professor Ahmed, I will also share my slides so you can go back to the details if you are interested by a specific theme here or a specific author or researcher in Tunisia. And also I can also assist in getting you in touch with them. So we have people working on the theoretical part of quantum information, like the robust control against noise of the quantum gates, as you can see here by my colleague Ghassan Dridi and his co-workers. So here a few recent publications. Then we have also people working directly on the implementation of quantum gates, like the C0 gates or the CCZ Gate, Amor Gedana, and colleagues. Then we have a quite large community working on condensed matter physics. Part of them are directly working on quantum materials, so quantum dots, either in theory or in experiment. So you have also here a few snapshots of the papers they have recently published. So they include, as you can see, various topics in condensed matter physics, also on quantum materials and topological materials, as you can see here, without going into all the details. Now, let me spend a few minutes speaking about what we are doing in my lab, which is the laboratory for atomic and molecular spectroscopy and applications. So the lab was founded in 2001. The main activities covers plasma physics, like laser-induced breakdown spectroscopy and the fluorescence techniques, with applications in biology, medicine, and environment science. Also, ab initio calculations in molecular physics and the quantum chemistry. And here in blue, the Rydberg states and cold atoms and quantum computing. So maybe this is more related to QST. To have an idea about the workforce, about roughly 40 people. About now, the number can be updated to about 500 publications with a good age index and a number of citations, and several international collaborations all over the world. So if you just one slide about the experimental activities in spectroscopy. These also are two publications covering the, on one side, applications to astrophysics and calculations of molecular species which can be observed in the interstellar medium, but also some experimental work on the use of lasers to characterize and investigate the properties of either like oils, etc., or but also applications in medicine, like looking here for specific pathologies. Now, let me go directly to the cold atoms and Bose-Einstein condensates part, which is more directly related to QST. We started this activity about 20 years ago. So you can here have an idea also about some references if you are interested in. The main idea is that with lasers, we can coherently manipulate atoms. So thanks to the interplay between internal degrees of freedom, which means excitation, disexcitation of the atoms, and their external degrees of freedom, motion, both are coupled. So by using the lasers and cycles of absorption emission, we can act on the motion of atoms. So we can accelerate them, we can decelerate them, so we can cool them, we can trap them. And the laser-cooled atoms have a very good properties that makes them very useful for sensing mainly, so metrology, but also quantum computing. Well, probably the following slides are a bit more technical, so I will go quite fast on them. But maybe if there is one idea to understand, even if you are not working in this field, is that imagine you have an atom and you shine a laser on it, depending on the on how large the frequency of the laser is compared to the frequency of the transition between the fundamental and the first excited state levels. So if the frequency is smaller or larger, we say red detuned in the first case and blue detuned in the second case, you can trap the atoms in the region of space where the intensity of the laser is maximal or minimal. Okay, so thanks to this interaction between the lasers and the atoms, you can we were able to simulate various situations in what we call atom optics. So where we can use atoms, use lasers, sorry, to split an ensemble of atoms into two parts, as you can see here. So this is the beam splitter. Or even atomic beam deflector, so to change the direction of the atomic beam, or instead of using like cold atoms. So what I mean here by cold is a temperature which is absolutely low. I mean a few hundreds of microkelvins. So this was achieved experimentally like 20 years ago, and now it's a standard technique in several labs. We do not have this experimental part in our lab, but we are able to do some realistic simulations. So if you go down with temperatures below 1 microkelvin to temperatures like a few hundreds of nanokelvins or lower, you can reach a new state of matter called Bose-Einstein condensate, a kind of giant or macroscopic matter wave. So it's possible to describe it with like kind of Schrödinger equation, including the interactions. We call it the Gross-Pitaevsky equation. Here also, I'm going to skip the details, so just to maybe to let you know only the general aspects of this work. So we could simulate the beam deflector, not in the case of not only in the case of cold atom, but also in the BEC. BEC stands for Bose-Einstein condensate. How to create the condensation in specific type of lasers, the so-called Lagergos lasers, in 1D, 2D, 3D lasers, and compare the shapes of the condensates, their topology, in comparison with the standard ones. Studying some specific aspects like finite number effects, like here. Maybe I will insist on one application in quantum metrology, which is the test of the weak equivalence principle. So the weak equivalence principle postulated by Albert Einstein is simply the equivalence between gravitational and inertial masses, which means if in the field of gravity you just drop two different objects with different masses, which can be very different, they fall in the field of the gravity with exactly the same dynamics and reach the ground at the same time. So this is the WEP, W-E-P, the weak equivalence principle. There are several experiments. You can find very interesting illustrations on YouTube. Here the video is not active on my presentation, but you can find it easily, and it's really impressive. An Apollo 15 mission to the moon, you can see one of the astronauts just dropping a hammer and a feather, and you can see them, the absence of atmosphere on the moon, falling exactly at the same time, and they reach the ground of the moon at the same time. So this principle was tested since antiquity, actually, to to very, very recent experiences or experiments, even on satellite here, like in 2017. And on the last row at right, you can see the sensitivity of this test. So going from typically 10 to the -2 to 10 to the -15. So the idea was to try to use these very sensitive and fragile but very precise objects, which are the Bose-Einstein condensates, to improve this sensitivity, or at least to obtain a sensitivity of the same order here as on the satellite, but on ground. So targeting like 10 to the -15. So for that, I go back here to the slide of the publication. What we use as like two objects, we use two Bose-Einstein condensates of two different atoms. So here, namely potassium and rubidium. Using the lasers and the force the lasers can exert on the Bose-Einstein condensates, be able to accelerate them to some point, and then they go through a free fall, and using interferometry techniques to be able at the end of the day to see if they reach the equivalent of the ground on the experiment exactly at the same time. So this is the idea. In the blue here, the rubidium atoms, the potassium atoms, the rubidium atoms here, acceleration over several centimeters, and then they go up like in the catapult experiment, and then they fall down on the gravity. So trying to reach this kind of precision with some technicalities here that I can skip. Just to mention that there are experiments also for which our output was useful. In particular, the tower in Hanover. So these are towers actually of several meters, like 10 meters of height, with a vacuum inside, and experiments like the one we are simulating using two different species are conducted in USA, China, and Germany. So this was quite successful, and as a follow-up of this kind of studies, we are just about to submit this month a new paper improving the protocol by showing that we can have a kind of specific control that improves the performance of this kind of experiments. So this is directly related to quantum metrology. So now just a few words about the quantum computing activity we started quite recently with the first work with the Raja Shamahi on the way to build up quantum registers, just to implement basically the integers here on as you can see here on this slide with like 5 bits or 5 qubits using the specific quantum states of a diatomic molecule using a sequence of lasers, femtosecond, then picosecond lasers, and you are able to show that we can like write and read the information correctly, to store the information about the integer numbers and to read them while photoionizing the molecule. Then more recently, we moved to the variational quantum algorithm applications for molecular physics, our field of competency. So the variational quantum eigensolver algorithm is a hybrid algorithm in which part of the calculation is done on a quantum circuit, so using the quantum gates, and the quantum set is propagated through the gates using Trotter-Suzuki decomposition, etc., and the measurement at some point. So then you come out with the first estimation of the energy of the ground state as a mean value of the operator. And then the quantum state is slightly changed using a classical optimizer. So here we take advantage of, on one hand, the power of the quantum circuit to go faster, thanks to the interferences and the selection of the value we need, and then the established techniques of optimization in the variational calculations, the classical variational calculations. What we did, so this has already been done actually and applied in several systems and literature. What we try to do is to add like quantum machine learning tools. So to add the quantum networks at the beginning to improve the quality of the ansatz, the guess wave function at the beginning. And I hope you can see here in this graph, the right part. So on the x-axis, you find the number of layers of quantum neural networks, so going from 2 to 8 here in this example. And on the y-axis, the deviation in energy with respect to some reference value. And what you can see basically is that this difference, the deviation is going down, which is good. And the first VQE value is in green here, so we start somewhere here, and we end up here close to the red line, which is the limit conventionally called the chemical chemistry, which is the accepted threshold to say that the calculation is accurate enough to be useful. So we have shown that to the cost of like 8 or 9 layers, we can reach this value. So this work is done by my student Selim Hamami, and it's under progress. Okay, so now the third and last part of this talk concerns the outreach activities, and it addresses in part the question raised by our colleagues, how to interest young people, high school students, to introduce quantum concepts. So for that, we have set up and founded the Quantun, the Tunisian Quantum Network. So here, as you can see, we were lucky because these letters are also the starting letters for Tunisia. So they just switched the M into N, and it gives us this nice name, Quantun. I have had the pleasure to found it with my colleague, Professor Siam Jaziri from University of Carthage 3 years ago. And we immediately involved young people, the students and the network by creating the youth branch of Quantum of Quantun. So it's Quantun Youth Branch. And since that time, the Quantum Youth Branch was very active. You can find these activities on the social networks, Facebook, Instagram, Twitter, LinkedIn, etc. So they have this page. And so we were involved in the celebration of the World Quantum Day every year. And this year in particular, the celebration of IYQ, several events. You can find the details on the web pages I just mentioned, with conferences, workshops, training sessions, hackathons, etc. Some of them were conducted in close collaboration with the Tunisian Physical Society, Tunisian Optics Society, and Q Tunisia, which is part of Q World, and also research labs. All these activities are also reported on the official website of World Quantum Day and IYQ. Just to give you one very short idea about the recent events we have organized this year in February and then in April, we are focusing more on training. So, of course, conferences and general talks are good, but they are also available elsewhere. So what we try to do is to bring people working on the field, like here colleagues Iyad bin Sliman from University of Carthage, who is a computer scientist working on quantum computing to deliver lectures and with hands-on and practicals for students. So with 2 sessions in February and in April of this year. So we are also involved in the Quantum Cities initiative. So we are on the map here, as you can see. Thanks to these activities of the Quantum Network and its youth branch. So, for instance, Tunis now is listed among the quantum cities in the world. And I hope that more cities in the region, of course, I know that thanks to the efforts of Professor Ahmed Younes, Egypt and specifically Alexandria is already on the map. I hope that other cities will join as well. So with this, I would like to finish my presentation, and thank you very much for your kind attention. Thank you.
Thanks very much, Dr. Murad, for this nice and very rich presentation full of research, but also all of these nice activities that has been going in Tunisia, and also all of these nice papers and work by the graduate students. So I'm now looking into the chat to check for the questions. So in the meanwhile, I can start the ball rolling by asking mine. So now, how, in your perspective and research, how quantum computing is helping Bose-Einstein condensate?
Well, I can address the question on both sides, either using quantum computers and quantum algorithms to describe the Bose-Einstein condensate physics, like solving the Gross-Pitaevsky equation. This is one way. The other way is to use the properties, the coherence properties of the Bose-Einstein condensate to make a kind of qubit and to use it as a part of hardware. It is not already the case. Cold atoms are already used. So laser trapped and cooled atoms and optical lattice are already used, and there are already companies working on that, and it's a versatile and very good technology, actually. Bose-Einstein condensate, not yet. First, because it's so hard to obtain. You have to go very low in temperature. It's very fragile, so it's not on the agenda today. But who knows? It may be possible within a few years. Sorry.
Yeah, thanks, Dr. Murad, for the nice answer. Another question which pops all the time about how often we can realize molecular qubits, qubits based on molecular states. I think Ala is nodding, so is also, yeah, because we discuss this question all the time. Yeah,
yeah, you know, well, first, how an atom can be a qubit. A qubit is basically a two-level system. While an atom has an infinity of states. So how an atom can become a two-level system, actually just by using a laser, so light, where the energy of the photon or the wavelength or the frequency matches exactly the transition between a couple of states. So you can ignore all the other ones. So that's the way you can describe or use an atom like a two-level system, so like a qubit. The ground state, excited state, 0 and 1. The same applies for molecules, of course, because a molecule is also a quantum system with quantized energies. The difficulty is that a molecule, even the simplest diatomic one, has, in addition to electronic degree of freedom like the atom, a molecule can vibrate and rotate. So it has a much richer spectrum. So it can be useful, as I have shown in one of the slides, for instance, to code integers, for instance, or any other information. But for that, we are using more than actually 2 states. But if if it is possible to identify a couple of row vibrational states and find the lasers that matches exactly that transition, of course, this is it can be very interesting, and molecules can offer much more degrees of freedom than atoms for quantum computing, probably. So it's promising, I think.
Yeah, thanks very much, Dr. Murad. And I think that's a nice effort also along with what Dr. Ahmed is doing. Perhaps Dr. Ahmed would like to comment on do you have any comment, Dr. Ahmed?
Yeah, actually, Dr. Murad is really a good friend. I had the honor to meet him a couple of times. Dr. Murad is doing very, very good job in Tunis and in the Middle East. So I hope I can see you very soon in Alexandria. And thank you.
Thank you, Dr. Ahmed. It will be my pleasure, of course, and also to meet with other colleagues and Dr. Taha. Thank you.
Yeah, thanks, Dr. Murad. And we also will be happy to welcome you in Alexandria as well as a speaker and a jury member, and also meet you in person again, because we have met in France a long time ago. So now it would be nice to meet you along also with Dr. Ahmed. And okay, so yeah. So thanks very much, Dr. Murad. I think if there is late question pop up in the chat, why we don't benefit from molecular orbitals to gain multi-level quantum systems. I think that was answered now, presumably, in the molecular qubits.
Yes.
Okay, so yeah, thanks, Dr. Murad again. And now we move to our next speaker, Alain Chancey. I'm just sharing my screen now. Yes, the qubits. Yeah, right, Greg. Yeah, that's.
Yes, I confirm, absolutely.
Okay, so our next speaker is Alain Chancey. Alain is going to talk about quantum education and also the research featuring sample-based quantum diagonalization algorithm, SQD. So Alain is the president of MolKet SAS. So it's our startup that's based in, which is based in Paris. MolKet is a member of QEDC network in the States and QEIC, which is the equivalent one in Europe, offering management, consulting, and AI services in quantum molecular dynamics, cryptography, neuromorphic computing with cloud-based hybrid HPC and the quantum computing platforms. Alain is a founder and is a CEO of Quant Alain Sassou and Alain Quant LLC, business management consulting startups. He's also a Qiskit advocate, IEEE senior member, society affiliate of the American Chemical Society, SES, and a member of the American Physical Society, APS, and a member of the Quantum Security and Defense, QSecDef. He's also among the advisory board committee. So he's a committee member of the North America Technical Institute, NATI in Virginia in the United States, which offers a professional certificate program in quantum computation. He's also was a panelist at the Quantum and AI Use Cases panel at QEDC in March 12 in 2025. He participated in the IBM Quantum Developer Conference in 2024. He's also keynote co-speaker of the Combining the Power of AI with Quantum at the World Artificial Intelligence in Cannes Forum, WAICF in 2024. He's also the co-author of the book Quantum Chemistry and Computing for the Curious, illustrated with Python and the Qiskit code published by PACT in 2022. He has over 30 years of experience in major enterprise transformation projects, and he also holds a master's degree from Engineer Civil Domaine in École Domaine de Saint-Étienne in France in 1981. Yeah, Alain, please, the floor is yours.
Thank you, Taha. Let me present. I will share my screen because it's the most effective way. And then quickly, I hope you can see my screen. I will move to the Yes, so great, sample-based quantum diagonalization. It's a great topic at the intersection of research and quantum education, and I will explain why. Now, my presentation is mine. The ideas are mine, but bear in mind, as a Qiskit advocate, I've got a positive bias toward Qiskit, the Qiskit advocate community. And so the ideas, the material is mine, but it leverages the good quality documentation from IBM Quantum. I just wanted to make it clear. So yes, in addition, so you see the cover of my book on the right-hand side. I would mention that more recently, in the last couple of weeks, I've been an active participant in the so-called early summer school, which was followed by early in July by the Quantum Global Summer School, QGSS 2025, sponsored by IBM. And I was a mentor, which gave me the privilege of helping out a number of participants, and some of them have made very good feedback posts about my approach to mentoring. And so, yeah, this is okay. So don't worry, there is no, okay, my presentation, there is no prerequisite. You won't see any equation. It's accessible to everyone, even if you have no background in quantum physics nor in quantum chemistry. So please stay with me. So this is the agenda. I will introduce quantum-centric supercomputing, then the SQD, and then two use cases which illustrate the cutting edge in terms of research. And then I will move on to illustrate how it is implemented, but in a way that is based on my own experience. Because one might ask, but Alain, who taught you? I mean, who is the teacher of the teachers? Who mentors the mentors? Well, this is my own experience. At some stage, you must become your own teacher. So self-learning, but not in isolation. It's really important to find a way to teach yourself, but not in isolation. So this is what I will illustrate with the last two slides, which are actually available on my public GitHub site. And so at the end, you will see that you can actually replicate the experiments, which was just cutting edge just a few months ago. Okay, let's move on. So quantum-centric supercomputing, what is this? So I give a definition which is extracted from a publication, joint publication by IBM and Pascal. So interesting because IBM, one of the leaders in the quantum computing based on superconducting loops, whereas Pascal is the neutral atoms. Now, interestingly, these two key players have entered a partnership, and they have defined a, well, first of all, they are very vocal, claiming that the future of high-performance computing is with quantum-centric supercomputing. And I will give a more precise definition. And they claim that it is the way to achieve near-term quantum advantage in chemistry, materials science, and other scientific applications. And in all my slides, you will see links to the relevant article or paper or video replay. Now, what is very simple, actually, a so-called quantum-centric supercomputer is comprised of quantum processing units, QPUs, graphical processing unit, GPUs. I'm sure you've heard of NVIDIA GPUs being the basic building blocks of the most powerful supercomputer in the world, and of course CPUs. And these are required, all of them together, to unlock the next generation of computing. So this is a definition extracted from an invited talk by Jay Gambetta, who is, if I remember properly, a vice president of IBM Quantum. Okay. What is sample-based quantum diagonalization? Now, I copy-pasted what I believe is a very good way of presenting this, the why, and it's a very good definition which doesn't require any knowledge of quantum chemistry or quantum computing. Basically, it's a chemistry simulation technique. It might be applicable with some effort to other fields, but definitely for sure, chemistry simulation. It uses the quantum computer to extract a noisy distribution. Noisy because of the imperfection of today's qubits. They are still prone to errors, and we are talking about the so-called NISQ era, noisy intermediate stage quantum computing. So we are still there, but and so the added value of the quantum processing unit is to extract a noisy distribution of possible electronic configurations of a molecule, or it could be but typically a small to medium molecule in the form of bit strings. Yes, that's a very neat way of viewing it. Again, you don't need to have a good knowledge of what quantum chemistry is about. And by the way, if you want to learn more, I welcome you to have a peek at my book, Quantum Chemistry and Computing for the Curious. And so the first stage, which is the sampling, actually extracting a noisy distribution, is called sampling from a quantum circuit. Okay, and then I call it smart error correction. The idea is to run an iterative correction entirely on a classical computer to cluster the bit strings around the correct electron configuration. So basically, it uses the knowledge, the functional knowledge of quantum chemistry, particularly symmetries, to fix errors that would not have been properly corrected, because we start to have error correction and error mitigation. We have not yet entered the era of the full quantum error correction, but we are getting there, and there are promising experiments. So nowadays, on the available, the most powerful quantum processing, quantum machines offered by, among others, IBM on their cloud, now you have got machines with typically 127 or 133 qubits. They are noisy, but there are algorithms which are being used in practice to a certain extent to mitigate these errors. But the SQD adds another layer. It's called, so they call it error recovery. I would like to, I've coined the term smart error recovery because it uses the knowledge of the use case, in that case, chemistry. And of course, we will show how it works. So this technique, for a large enough noisy quantum computer, yes, we need, and this is what we have today. We have a very large, in terms of number of qubits, plus the ability to run up to, quantum circuits with a depth, that's the number of gates you can put one after another, of several thousands. So it starts to be, we have moved away. We are at a very interesting stage, in my opinion. It's the end of the pioneers era, and we are entering the so-called utility era, where we start to have experiments which are very promising and give at least some claims, so a glimpse of practical computational advantage. So So this technique has the potential. So it's still not proven, but there are hints, very good signs that yes, SQD could perform more efficiently than classical approximation methods. However, it has not yet been proved, and it is still I would say, a bet or a hope at this stage. Again, I give a link to this where I copy-pasted this, what I believe is a very good definition. Okay, so the first use case from IBM, Cleveland Clinic, and RIKEN, who have, it's a university in Japan, and they are lucky to have currently the most powerful supercomputer. I think I pronounce it right, it's Fugaku. And so IBM provides Heron, which is one of the most recent supercomputing quantum processor unit. Cleveland Clinic, they're bringing the knowledge of the quantum chemistry, quantum molecular dynamics. And so the three of them, they have managed to simulate, on one hand, the ground state dissociation of N2, which is nitrogen, and more impressively, the simulation of so-called iron-sulfur clusters. Now, on the left-hand side, you see, and this is again from I give the sources at the bottom, with the well-known and well-practiced variational quantum eigensolver, VQE for short, which, by the way, is also introduced in my book. We have use cases pertaining to hydrogen and lithium hydrate. Well, the bad news is that on today's quantum processing unit, even the most recent one, it would take 3 million years, I repeat, 3 million years to perform a meaningful simulation of the iron-sulfur cluster. So basically, well, it's hopeless, right? Even on fault-tolerant QPUs, which we don't yet have, we hope we will have those fault-tolerant QPUs as early as 2029, in 4 years. That's what IBM have promised. Well, and with a better algorithm, the quantum phase estimation, it can be proved mathematically, theoretically, that you can get the accuracy that you wish, you aim, simply by increasing the number of qubits. There is a number of caveats, particularly whether it's physically feasible to measure the phase below a certain level. But basically, even on the fault-tolerant QPU, which we don't yet have, with a better algorithm, quantum phase estimation, it would require 13 days. That doesn't seem realistic, because honestly, I mean, in a few years, we could hope for a quantum processing unit capable of running useful algorithms for several minutes, maybe a dozen minutes, something like that. But wow, 13 days. Because remember, well, or at least for those who discover the topic with quantum computing, it's not as easy as classical computing, where I just, okay, no big deal. You just do a dump the current state, okay, and you reset your computer, and you start from where you know. No, it doesn't work that way, unfortunately, because in order to do that, you would have to make measurements, which means you would have to redesign your algorithm in the first place. You cannot interrupt and save an intermediate state that easily. And so 13 days looks not realistic at all. Now, the excellent news is that within a quantum-centric supercomputing framework, so again, I mean, it uses the best, it's a best breed approach, using the best, one of the best, supposed to be best quantum processing unit from IBM, together with the most powerful supercomputer available in the world. Thank you, Riken. Plus, referring to a previous presentation, better than a multidisciplinary team, a team which integrates different expertise. Well, yes, there was a great success, the ability to run in just about 2 hours SQD and to achieve that simulation. And the authors of the study claim that their result gives a better quality in terms of accuracy than using only classical, that is only using the supercomputer. So I'll give the references at the bottom. So this is very promising. Okay. Unfortunately, I would say it's only those who can access these kind of resources that could try and replicate the experiment and confirm whether this is indeed the case. So the good news is that there is another use case. So this time it's Lockheed Martin and IBM. They also conduct chemistry simulations with SQD. And it pertains to the dissociation of 2 different states of the methylene molecule, CH2. So there is the so-called ground state triplets and first excited single states. And so they have achieved that with using 52 qubits. Now, it is impressive. This was done, I think, in 2024. And guess what? During the QEgypt Quantum Global Summer School, sponsored by IBM Quantum, one of the labs, Lab 3, we were given the opportunity for free, up a few minutes, part of the free plan. The participants of the QEGSS were given the opportunity to run experiments or simulation experiments on a much more powerful quantum processor. IBM Torino, that's the nickname, for example, has got 133 qubits. And it's available. So Lucy, this is something very impressive to imagine that just a few months after a cutting-edge publication was published using the most powerful quantum processing at the time, just a few months after, every participant in a big event like the Quantum Global Summer School could actually replicate this experiment with a QPU with a greater number of qubits. So in terms of quantum education, I think this is absolutely amazing and fantastic. It's a huge opportunity. And so the purpose of their effort was to benchmark quantum algorithms, plural, for accuracy and performance. If I let me summarize what quantum chemistry is about in a nutshell. Quantum chemistry and by extension quantum molecular dynamics is about designing algorithms, well, hybrid algorithms, classical quantum, and why not with AI in addition, that let you reach the so-called chemistry accuracy, which is 1 millihartry, but in a way that is achievable. So and so the science between quantum chemistry and quantum molecular dynamics is about designing the right models that gives you the required accuracy, because otherwise there is no added value. You need to reach that accuracy, but at a reasonable cost. And the challenge is the following: is that as the number of particles, i.e. electrons, in a chemistry system increases, unfortunately, the algorithms which work, they work well, their cost in terms of compute resources and time in particular, these algorithms, classical algorithms, they tend to, the amount of resources, memory and time increases exponentially most of the time. And so yes, so that's a challenge, and with SQD. So let me give you an idea what's the figure at the bottom left. So there are two states, and the orbitals are represented by these ellipse kind of things, and you see there are arrows up, down. Well, it represents the spins, because that's the interesting part. In quantum chemistry, you not only have to deal with electrons in different orbitals, but also the fact that electrons are fermions, and they can have different spins, and so depending on the way the electrons, their spin are opposite of one another, like on the top part, the singlet. Well, there are two different configurations, but basically 3A1 and 1B1, the two electrons have opposite spins. And the triplet, well, the two electrons occupy two different orbitals, but they have the same spin. So the overall spin of the triplet is one. Okay. So and what is it for? So it's important because so for rocket plume chemistry, it's important to figure out very accurately, as accurately as possible, where the two states, the singlet and triplet, where they are exchanged. And in the diagram on the left, you can see a number of curves. So there is the SQD in red. The CCSD and SCI are two well-known classical methods for modeling molecules. And what's interesting is SQD in red, at least part of it for bond length, so it's a horizontal axis. For part of it, you can see that the red dots, the red curve, in other words, tend to be almost as good as the SCI, because in quantum chemistry, I mean, the lower the better, okay? So the lower the energy, the more accurate. And in particular, there is, I guess you can see, there is, with the red, there are actually two drawings, one with like triplets, three thingies, and one with just the dots. And you see where it is, there is a square, and I've written first order phase transition. You can see that the two red curves, they intersect. And this is where the so-called first order phase transition occurs. And it matters to be able to accurately model this event. And so at least with the resources that were made available to the IBM and Lockheed Martin team, they were able to, and this is how they demonstrate, basically to approach, compete with the one of the best method, SCI, which is I would say an affordable method to have accuracy. So I give all the credits and all the references. So in a nutshell, the authors claim that SQD accurately captures the first order phase transition in a ground state where the singlet and triplet states of the CH2 molecule are exchanged. So it's quite an achievement. So just to know that, as I said, we are in the so-called utility era of quantum computing. And IBM have, based on their huge experience in other fields, like in high-performance computing, but also I would say in information technology and business related applications of computing, they have put forward a method, a framework to somehow standardize the way we should think of designing algorithms. So on the left-hand side, I've indicated in the column, but the purpose. So the first step is to map classical inputs to a quantum problem. Now, this may be, in my opinion, the most important step, because if it is made in a not so smart way, then the following steps just impossible to achieve. And on the right hand side, the method. So for quantum chemistry, so this method Qiskit patterns can be applied to all different use cases, not just quantum chemistry. But in the context of quantum chemistry, so we generate an ansatz, and this was nicely defined in an earlier presentation. Ansatz is basically a starting point, like akin to, it's a German term, but it's akin to assumption or starting point. And in the context of quantum chemistry, it's basically a quantum circuit, which is supposed to be a good starting point, and for estimating, in that case, the current state, but it could also be for estimating the excited states. The second step is to optimize the problem for quantum execution. So in terms of method, it boils down to so-called transpiling, which is another word for compiling the ansatz for the backend, that is the quantum processing unit on which you hope to run your or simulation. The third is to execute experiments, plural, using Qiskit primitives. Yes, and this is what differs between practical quantum computing and classical quantum computing. In classical classical computing, just run usually one run and that's it. No, with quantum computing, you have got to run a number of times the quantum circuit to get a so-called distribution of possible states. And if the algorithm is properly designed, then the good results would statistically have more likelihood to show up. And so it boils down to drawing samples from the ansatz and the Qiskit framework. They provide two primitives. One is sampler, the other one is estimator. Okay. And last but not least, it's the whole purpose of this discussion, post-process and return results to classical format. And this is the so-called self-consistent configuration recovery loop. So this is what I call the smart error correction. So basically, it's a clever way of leveraging the knowledge of the topic, the symmetries in the context of quantum chemistry, to fix errors. To fight against the noise, which is nowadays unavailable. We don't yet have the error correction. Okay, I'll give the references. So this is a couple of nice diagrams extracted from the documentation. I give the references. On the left-hand side, you see it's a new FFSIM. Don't worry, I give a glossary at the end of my presentation. So those who are interested to know what does LUCJ mean, it's explained in the glossary. But basically, at the beginning, it's classical, and in the middle, it's quantum. So it's basically running the quantum circuit. Collecting so-called configuration dictionary, and then at the end it's again classical post-process with SQD. Okay. Now the trick for those who want to have a more detailed view is, but it's quite clever. Is I would say it's akin to divide and conquer. Basically, solving the Schrödinger equation, which is the basis for working out the evolution of any quantum physics system, in particular in quantum chemistry. It boils down to solving a big equation with a huge matrix and finding out the so-called eigenvectors and eigenvalues. And the catch being that these matrices are much too large in practice, even on the most powerful supercomputer in the world. So the idea is that to break it instead of solving which is hopeless if the size of the molecule is just too big. The idea is to project, so-called project the equation, the Schrödinger equation, on some basis, and not just one, but a bunch of them, and then it becomes much easier classically to solve these equations. Okay, I won't go into detail, but I give the right references. So what's interesting, by the way, is that this method differs from the so-called variational quantum eigensolver or the QEOA approaches, which relies on the gradient descent. And the challenge with the gradient descent is unfortunately the so-called barren plateau. So as the dimension of the space is increased, it's like a plateau, and it's very difficult to find a minimum. But this approach is different. Okay. Okay, I won't go into detail. I think I would jump to the practical illustrations. So the way it works, and guess what? I will be able to show you Jupyter notebooks, which are published on my GitHub site. So basically, these are definitions from this publication. So yes, so it's something I mentioned earlier on, but to understand the singlet, the excited state, the 2 electrons in a carbon atom. So there's 1 carbon atom and 2 hydrogen atoms. The 2 electrons are paired, and 1 orbital is empty. So this one is empty there, the 1b1, and there this 3a1 is empty. But the 2 electrons in the carbon atom are paired. Okay, they are one is with a spin up, and the other one spin down. Okay, with opposite spins. So basically, the PyCF atom configuration, PyCF again, it's explained in a glossary. It's like Python. It's a very popular package, open source, to perform classically simulations of relevant to quantum chemistry. And quantum chemistry, by the way, existed long before quantum computing was available. Quantum chemistry is theoretical chemistry for ab initio, from first principles. Okay, so I will jump to the. Oops. So I guess you can see. Yes, the singlet. You can see. So this is. Can you see, Taha? Can you confirm? You can see.
Yes, I can see it. Yeah. So
it's available. It's open access. It's my own GitHub, Alexandria SQD, and there is a bunch of so under the heading SQD, and there is a bunch of molecules: CO2, H2O, LIH, N2, which was topic of the Quantum Global Summer School. But this is my simulation for the singlet. So basically, so it's well documented. So if you want to experiment, you just have to. You could do that. You don't even need to install anything. You could use Google Colab or some other environment, and basically grab the SQD underscore Alain.py, which is a file which contains a Python class, and any of those Jupyter notebooks, and run them. What's fascinating is the I think fascinating is the is with which it was done. So to work out the configuration, guess what? I asked ChatGPT. Asked ChatGPT, give me the PyCF configuration for the singlet CH2, and it gave me okay. So no big deal there, and just and then it's just so there is the configuration of the. So this is a fairly large quantum processing unit. That's got 133 qubits. And the trick, it was very well explained during the summer school, is to have a smart layout where the two different spins are implemented with kind of topology. I won't go into details, just to say that it is fairly easy for anyone to, and this is, I think, quite exciting. Anyone can rerun the experiments. Of course, to make it feasible, I just used a so-called basis set, which is requires much less memory than the one which was used by the team. But nevertheless, yeah. So it's done automatically each step. So there is one method for each step. And this is where it starts to be fun, in my opinion. And when you see the iterations, now the amazing thing is that you don't even need to spend part of your budget, which, by the way, IBM Quantum, they make it really affordable, because for free you can have up to 10 minutes per month, okay, to run stuff on actual quantum processing unit. But SQD is so effective that you can actually start with, instead of having a bit string which comes out of the output of a quantum processing unit computation, you can actually start with a random set of a bit string which is generated randomly. Okay, and so here I will move on to the graphic. It's much more fun. So so on the left hand side, you can see. So we start with a very crude approximation, and then fairly quickly look at how fast it goes in just 4 iterations. Boom, and this is the 10⁻3. It's the milli-Hartree. It's so-called the chemical accuracy. So boom, in just 4 iterations. Well, it takes something, I don't know, on my laptop, it takes like 10 minutes or so. So it does take time, but wow. You get with SQD a result which is better than the one which is required, the chemical accuracy. On the right-hand side, it gives an idea of the average occupancy per spatial orbital, and it's consistent with the expected view. I won't go into details, but I want to show you the, so this is the singlet. So now let's have a look at the triplet. So it's very similar, but at the end, it differs. So it struggles a bit more because there are 10 iterations, but it does work. And on the right-hand side, you see it reflects the fact that in the triplet states there are 2 electrons which are opposite signs. What I find fascinating is that this you can do it yourself, and this is how, by the way, answer to my early question. Some people might ask, but Alain, how do you? Who trained you? How? Okay, very simple. I took part in this event, the Quantum Global Summer School. But in order to qualify to become to be entitled to be a mentor, I had to be successful in the so-called early summer school, which was open only to Qiskit advocates. By the way, it's Qiskit advocates. It's a community of which supports people like me who have actively and significantly contribute to the Qiskit work. So I was not on my own. Fortunately, I had fellow Qiskit advocates to compete against. But in order to master the topic, this is what I did. Okay, so I gathered the documentation, which, by the way, is provided at the end of my notebook. All these references, and then I modified an available Jupyter notebook published by IBM, and I give the reference. This is the one, and I based on that I replayed it, and this is the best way to learn. So I would say it's my own. I hope my way of mastering the topic. In order to be a good mentor, I've got to master the topic, and the best way to master the topic is to be able to reproduce such experiments with Python and QEgypt and other libraries. And so that concludes my presentation. I would say that as a gift, I give you at the end a glossary. So for those of you who wanted to know, but what is Alain talking about? What is FFSIM, LU, CG, what is PyCF? Okay, quantum-centric supercomputing. It's all explained. SQD, and also this terminology. Okay, it's all explained. Plus, I give you an extensive bibliography, and it's a very interesting topic. And of course, I do include my own book at the end. So that concludes my presentation. I'm open to challenging questions. So we stop my presentation now.
Okay, thanks very much, Alain, for the nice presentation. Saskia Blom, she said it's not a question. So Saskia, you can also please ask if you like. Yeah.
I just waited until the end of the very interesting presentation just to share something that maybe some of you might find interesting, but it's not a question. Sorry.
Yeah, that was. Yeah, thanks very much for your announcement. That's really appreciated. So any questions from other audience? Okay, if not, I would like to ask myself what, okay, Dr. Murad is asking, is SQD an alternative to VQE for all systems?
So first of all, as I said at the beginning, SQD was invented very recently, by the way. It's derived from another hybrid method, but primarily for chemistry simulations. Because SQD, basically, the interesting part, which is rather new, is this smart recovery procedure. Well, I guess one could combine this recovery procedure together with VQE. That would be maybe one way to make VQE work better. Unfortunately, and this is my own experience, by the way, this was shared in my book as early as 2022, in the case of chemistry, unfortunately, mapping successful classical approach, okay, mapping that into the casting that into the quantum computing arena is very expensive because one has to make a very expensive mapping between fermionic and bosonic statistics. I won't go into details, but this explains why, unfortunately, the number of so-called Pauli gates becomes completely crazy, like millions of Paulis. Okay, so the number of different quantum circuits that must be run becomes completely crazy, I say. And the other catch also, which was pointed out a number of years ago, is that in order to reach the chemistry accuracy, which is 1 millihartry, the ansatz must be close to the exact answer by 1 part in a million. Okay, and so sometimes, so I did succeed in some earlier events sponsored by IBM because I took as an ansatz the exact solution, right, and then I ran VQE, and wow, yeah, it works. But no added value at all because, okay, so the challenge with VQE, at least for quantum chemistry, is that basically it's hopeless. However, it has been shown, including by IBM, that by casting, for example, the Simon's algorithm or Shor's algorithm into a quantum machine learning kind of problem, then this kind of method works. But it's a specially crafted use case. Okay, so it is also, it has been shown by a number of world-class experts that unfortunately there appears to be no generic quantum advantage with VQE. But that doesn't exclude the possibility that there could well be efficient, successful VQA implementations for specific use cases. Now, it's an open topic whether such use cases exist and are practical value. So I would say SQD is a better candidate. At least that's the view put forward by IBM, and I endorse this view than VQE for the field of quantum chemistry. But for other fields, I don't know, for instance, for optimization or for finance, I think it's an open topic. So that's my answer to this very good question.
Yeah, thanks very much, Alain. And for also Dr. Murad, we are trying also some use cases using SQD because also the good candidate does also optimize pre-processing classically and remove the overhead of VQE, especially on molecules like CO2 and so on. And also SQD is like a magic tool between, for example, VQE and the phase estimation and so on. It's like there is open question because it's a new algorithm from IBM, so there's a lot of collaboration is open about this new algorithm. So thanks very much, Alain, for the nice presentation and the nice use case presented on the sample-based quantum diagonalization. Thanks a lot. And for the audience, feel free to wait for the material, for the PPT file of the presentation on the folder that will be shared shortly after the event. Okay, now we move to our next speaker, Dr. Mohammed Amin Moradi. Just allow me to share my screen. So Dr. Mohammed is going to present how to stimulate and enhance quantum education. So Dr. Mohammed Amin Moradi is, sorry, there is a typo here, he holds a Bachelor of Science in Chemical Engineering from the University of Tehran. Also, he has a Master of Nanomaterials from the Sahand University of Technology. He has a PhD in Functional Nanomaterials from Eindhoven University of Technology. As he held a postdoctoral research position focused on advancing on advanced electron microscopy, cryogenic and liquid phase for materials self-assembly. He has multiple professional experience, like he has participated in the National Public Education Program for Nanotechnology, circa 2005 until 2010. And also currently he is a program manager for the Quantum Talent and Learning Center in Eindhoven. He worked as a model developer at Rabobank, which is one of the major banks in the Netherlands, and also worked as a design engineer at ASML, which is also the well-known company in lithography machines in Europe. So I'm now stopping sharing my screen. Welcome, Dr. Mohammed, and the floor is yours.
Thank you very much. Can you hear me, Taha?
Yes.
Yes. So I'm going to share my slides. That this is the right way.
Yeah, it's a bit tricky in Google Meet for sharing the slides.
Exactly. We usually use Teams in the Netherlands. So
yes, indeed. Yeah.
So trying to put it on the slideshow, and then yes, seems like it's working. Okay, thank you very much for having me today. I'm actually just coming back from holidays in Tunisia. It was my first journey to Africa, and I was surprised with this nice presentation from Professor Murad here, that I learned a lot, as I had in my mind, okay, so I should have some friends in Tunisia to ask about what quantum developments are happening there. So it came as I wished. Thank you very much. And I was also very surprised with the name of Murad. That is apparently very common in Tunisia. So not only for people, for also places are named after that. So I felt with my last name being Muradi, very, very familiar and to the community in Tunisia. So yeah, maybe.
Also, it is a popular name also in Egypt. So if you go there, you will find.
Oh yeah, okay.
Yeah, the same name. This name is are really common also there. So
you can be Muhammad. You can be confused with a big owner of hotels and
yeah,
five-star hotels in Tunisia.
Yeah, the
So
Al
you can be
Muradi
taken for a
Palace,
billionaire here.
Yes, I was staying next to Al Muradi Palace, and so I know the story a little bit. I heard from the people. Yes, so with that background, so I prepared a few slides focused not on the Netherlands quantum plans, which is very big, like 600 something million. Project of Quantum Delta is going on here, so you probably know about that. But just focusing on the little bit that I am working with, which is the Quantum Talent and Learning Center in Eindhoven. And I think a phrase like a quantum center for everyone with any background would be a nice advertisement for that. So we hope that at least in our region, which is suddenly the Brainport region in the Netherlands, and a lot of engineers and like sharp and smart people are invited here to build up a technology, sort of Silicon Valley of Europe in Eindhoven. So this center is there actually for everybody who feels like they have a question to join and connect and find their answers. So I'm working as the program manager there, meaning that I will not discuss the scientific details here, but I will introduce a little bit of the research groups at the Eindhoven University who are developing the science so that you can contact them later on. But before that, I want to set this up. So as I said, the talent and learning centers are physical centers, as you see in the background in Eindhoven. It is at the QEgypt building, placed at the Eindhoven University campus. So it is a qubit. You can only go through it via tunneling. So there is no door. So if you're in the Netherlands, you want to visit us, you should contact us. We will help you in any ways. So in the Netherlands, I have to say that for everybody who is not familiar with the educational system, there are 3 levels of universities, I would say, and the Quantum Talent and Learning Centers are specifically meant to work at the interface of these 3 levels and help the students to come together and gain experience for later work in the quantum ecosystem. And the TLC in Eindhoven is actually placed in between Eindhoven University of Technology, Fontys University of Applied Sciences, and Summa Vocational School. And it is supported by Quantum Delta NL, which is the big initiative for developing quantum in the Netherlands. There are 4 TLCs, as I said. In Delft, Leiden, there is one. In Eindhoven, there is us. In Enschede and in Amsterdam, there are the others. So this is the baseline of my talk. So it is not going to elaborate on the quantum plans in the Netherlands, but on our center, which is focused on quantum learning. Okay, I see two different slides. I read the title, so make sure that you all see the same slide as I see. The TLCs are part of the human capital plan of Quantum Delta NL. So as you can see on the bottom right of this slide, Quantum Delta NL works on a big plan consisting of 3 catalysts for 3 main research domains on quantum computing, quantum networking, and quantum sensing. Through 4 action lines, the first one focused on easing research and innovation, second one on quantum ecosystem of startups and growing companies. The third one, which the talent and learning centers are part of, is focused on human capital development. And the fourth one is on the societal impact, like what is the aspects of quantum on the society, what ethical and legal aspects needs to be developed and set for the future of quantum technology. So what are the goals of the talent and learning centers? They are supposed to increase awareness of quantum developments within the 3 levels of education, as I mentioned. They're supposed to facilitate challenge-based learning, which is a new topic to the university and to our educational system, which needs less supervision from the supervisors and is based more on the challenges that are coming from the business and quantum companies. And at the third one, we need to be ahead of fast-growing ecosystem, meaning that we need to recognize the need for the human capital and try to teach them and prepare the talent in advance so that in a few years, let's say 3 to 5 years, when the startups are there and on the scale-up step, they can find the human capital that they need. So what do we offer right now, regardless of what we will be able to do in 3 years? Now, we have the Applied Quantum Technology Master at the Applied University level at Fontis, which I wanted to put it first. It is going to be run between the 4 applied universities of the 4 hubs that I mentioned, and it will start this September, and it is unique in a way that all these 4 applied universities are offering their expertise as part of this joint Master Applied Quantum Technology. So one student will study in all these 4 applied universities. So how is that connected to the TLCs? You will find it a little bit later. So we also specifically offer the Quantum Safe Cryptography Minor, which is a short course in the format that is accepted by the applied universities in the Netherlands. So specifically students of applied universities can follow this, and it will also start this September at Fontis University. So in parallel with that, the other applied universities have other minors that I am not going to mention them here, but you can learn from them from their websites, or Taha can help you find them. We also do offer some products or services, quantum services to younger generations within the TLC at the On Deck Fabric, which is sort of like a student's learning workshop for science. They have just launched a very interesting half-day event for the students of secondary schools. We have the student teams called Education, which will be introduced by Shortwijgers after me. And I won't speak much about that. Working on using game rooms to make people aware of what quantum concepts are. And we have recently helped a kids author to write a new book for the age of, as she says, 6 years to plus 99 plus. So for everybody who want to learn about quantum concepts in a very engaging and interesting way without any background. So these are the projects and products that are now available, let's say. We also initiated an annual quantum education event last year, and we are going to have that within the network of the TLCs this year as well. It will be held in the TLC Delft Leiden this year. So soon you can follow the advertisements for this event. These are actually part of the work that we have. I selected a few. We also have other smaller or bigger projects, and I'm now going to tell you how we do this and how we actually come up with these ideas and how we progress with these ideas. So we have one of our most important pillars of the activities and developments at the TLC Eindhoven is experience sharing discussions. So we talk to everybody, not just a single way, a monologue. We normally try to present what we do and also hear what questions people can have. So we ask for their 3 years plan and needs for quantum technology. We ask whether we can facilitate them with a training program, short-term, long-term, whether we can offer them a feasibility study based on the departments that we work with, because we work with applied physics department, ICT department, entrepreneurship department, and at these departments we have the potential to make groups working on feasibility studies. We also ask them whether they need an educational setup for their company, for their institute, where they want to offer a specific course, an onboarding course, or other types of trainings that they have in mind. Specifically, startups normally do not have the capacity to have a separate onboarding or educational program when it needs a setup for that. So we try to engage there and offer them the opportunity. And we actually ask them whether we can share a talent pool for later if they want to scale up and work with us actually in long term. So after experience sharing meetings, or beside that, we are developing a quantum education and development lab at Applied University Fontis, where we discuss and plan the setups through the available formats of projects that students can engage. So teachers and the students work together on developing these setups. There is a recent update published by Dr. Saskia Blom here in this meeting. Also, she is there, so you can read about that and see what we have available at the moment for quantum education setups. So these include like very first experiments that you need to do with MV centers, and also some more that I invite you to actually read this update from Saskia and the team. So the third pillar for our TLC activities to bring those products are the student teams. And we are very proud actually with this initiative, because normally student teams, if they're not supervised by a specific supervisor or professor, are not actually at the first level of research and development at universities. They're considered as side activities mostly. In Eindhoven, there are also some groups and initiatives that boost these kind of activities, like the Eindhoven Innovation Center at TUE. But there also the challenges are not coming as you expect with the serious high-tech questions. For example, there are no quantum team projects available at the Innovation Center, as far as I know so far. But at the TLC, we initiated so far 2. Education is the first one. QEgypt focused on building a magneto-optical trap is the second one. And the specific thing about these student teams is that the organization is being done by the students themselves. And they learn by working for, if I want to simplify, a mock-up of a startup. So they're supposed to invite actually students from different levels, and then when they're working together, they will learn how to do that, and they can either develop on this initiative to a real startup, or they can actually leave the topic they're working and be a ready, quantum-ready team for other challenges that are coming from the ecosystem to them. So a very good example is education. Shorty's gonna introduce that after my talk, and I'm very proud of these two and this initiative. So in one picture, the TLC Eindhoven, the blue box in the middle, looks like something that you see here. So it is consisting of the EHCI, the Henry Casimir Institute at Eindhoven University, the Fontys Applied University, and Summa College. And we have the CBL labs, we have the development labs, and we are setting up a training for the clean rooms together with the other MBOs within the Netherlands. So we have projects, as I said, with On Deck Fabric, education is coming, the Mini Mavericks publishing group is working, the professional master that we have some existing courses at the university side, and some projects that are going on at Fontys University. Now I think it is the moment to mention a little bit about the research groups at Eindhoven University for the people who don't know about them. So basically the quantum computing lab of Professor Servaas Kokkelmans on ultra-cold Rydberg atoms is placed in Eindhoven, and they're working on making a full stack Rydberg hybrid quantum computer. Together with Servaas group, there is the group of Professor Ildefonso Tafur and Chigo Kunkuo, recently becoming a full professor. They're working on quantum communication based on photonic system integration capabilities, and with them, actually, we are connected for developing on the quantum safe cryptography minor, and the other case-specific education modules. So within or under this quantum communication center, they are developing the Eindhoven testbed for quantum safe communications. And I think this is a very brief introduction of the TLC in Eindhoven, which you can find the details, specifically the interviews that we do with the figures, quantum figures in Eindhoven every now and then. You can follow us on LinkedIn, and you will be updated on all our activities. So this was actually the very short introduction I prepared for this meeting, and I think we'll be happy to help and join any conversations with the people who are present in this meeting.
Well, thanks very much, Mohammed, for all of this nice work and a nice illustration about the role of quantum TLC, and also all the wonderful efforts which are done at TLC in Eindhoven as well. So we have a question from Dr. Murad. I'm interested in Cubium project. Is there a possibility to discuss the opportunity to duplicate the implementation of a mod for students in Tunisia?
I think it is a very good discussion to have. If you are open, I prefer to have it separately out of this meeting. But yeah, so I'm very interested to discuss this.
That's great. And then I can also ask a question myself. So when you start your PhD, what will happen if you find a TLC? Would it make a difference for you? And if yes, how it could be?
Yes, very nice question. So we have PhDs actually at the Eindhoven University in this case, and we ask them to contribute to either as supervisor to the teams, or actually help us when we want to have courses for the companies. These are the types of work, or we can offer them internship students if they have projects. So there is something coming. It is very interesting to know that actually in Eindhoven, at least at the university, the fundamental research is going on at Eindhoven University, but there they need a lot of work for the setups to develop, and also which are not very cheap actually for a researcher, and there you see that they actually don't know that they have so many good engineers at applied universities and Summa College who can help them. So what we do at the TLC, we make this bridge. So we had some examples, and now the fundamental researchers are thinking of oh yeah, we shouldn't have wasted so much time on building everything ourselves. There are people out there who can help us and who can speed up our research. And with this, actually, they can have quicker outcomes and publications. So,
yeah, indeed, that will make the life of the PhD students much easier indeed, and also more collaborative. Was a nice network and work they can have from colleagues from applied science universities. Okay, another question: what do you see the impact of the new master on the workforce? How do you envision this in Eindhoven, and how the companies, for example, are feeling about this?
Well, let's mention that I am not the main responsible for the development of the applied quantum master in Eindhoven. My colleague Lotte Spaniers is the representative, and she knows everything about it. As far as I know, we have had a workfelt committee in the development process. So the companies in this workfelt committee have been discussed 2 times at the beginning and at the end of developing the courses and plans for the course. And the considerations they've had, questions they've had, needs they predicted from the companies and the ecosystem were discussed and have been connected with the base of these students, because not all of these students are coming from a physics or applied physics background. They're coming from different backgrounds, and they're going to be directed into different tracks of quantum software, quantum hardware, and these different tracks actually will need different backgrounds and essentials. So they will be all enriched on their needs and weaknesses in this course.
Yeah, thanks very much, Mohammed, for highlighting this. I think the master is a new opportunity and a good opportunity to bring the new workforce. And I was happy also to work with Lotta for in the past 2 years as well in the development phase. And thanks for your insights as well and the nice presentation. And we are looking forward to hear the product of the TLC, one of them, QEducation, from shortly as well, and hear how this new idea for making students responsible for startups can help boosting quantum education.
Thank you.
Okay, thanks very much, Mohammed Amin Muradi. And now we are going to move to our next speaker. So just allow for me to share the screen. Okay, our next speaker, Sjoerd Vijgers. So hopefully I pronounce the name. I will need to practice it. So maybe Saskia can help me in the correct pronunciation.
Sjoerd Vijgers, sir.
Yes, thanks.
Yeah, thanks. So Sjoerd is much easier actually, just only to get the correct spelling rightly.
Yeah, it's a really Dutch name.
Yeah, but I mean I don't hear it quite often, so that's but it's very nice name indeed. Okay, so welcome Sjoerd. So short bio about Sjoerd. He graduated with a Bachelor of Applied Physics from Fontes University of Applied Sciences in last December. He had an internship at Quantware focused on quantum chip packaging and the bonding techniques. He also co-founded Education in August in 2023. Also, the aims of education is to educate high school students, companies, and also the general public about quantum mechanics through quantum video games. Okay, welcome, Sjoerd. The floor is yours.
Yes, thank you. Let me see how I can present.
Yes, always tricky in Google Meet. So that's
pretty sure you can see it now, right?
Yes, we can see your screen.
Okay.
Yes, presentation is visible.
Thank you. At least that I could give my talk here. As you said, my name is Sjoerd, and I'm part of the student team called Education. And the goal of my talk today is actually to show you how to inspire the next generation with video games. Before I do that, I want to thank the Fontes, the TOE, AAC, and Quantum Delta for supporting education. And actually, specifically, he is also present today, Mohammed Amin Muradi from the TLC in Eindhoven for his support during our project. Actually, to get the answer how to inspire the next generation with quantum video games, I will go through a couple of hoops to set up the base. So first, I will introduce myself. You did that quite well, actually. Thank you. And then I will introduce education, as this gives a good example on how you can do this. So as you said, my name is Sjoerd Wijgersen. I hold a Bachelor in Applied Physics. In August of 2023, I co-founded Education with 3 fellow students. And currently I am responsible for the talent acquisition of Education and also of the quality of the lesson material we use in high schools. In this meeting actually is another founder present, which is Paste. Yeah, I cannot see the webcams, so I think he is waving or something. So quickly, what is Education? Education is a student team with currently 31 students, which include 8 board members. And these 8 board members actually have weekly meetings focusing on the direction of the student team, keeping it in line with our goal. And the goal is to make quantum more accessible and engaging through the power of video games. And you can already see that in the pictures I have over here. You have on the left, you have a classroom where the children play quantum games. And on the right, you have an event in Eindhoven called Night of the Nerds, which is also very busy for children. And you can also see that we use the quantum video games to play and explain the quantum concepts to them. When we actually started in August, we had a decision to make, and that was to make our own game, our own quantum game. But before we did that, we actually went online and looked for quantum games. And what we found is that there were over 380 quantum games with quantum in the title, quantum power-ups like tunneling or superposition, quantum in the description, or just educational quantum games or apps. So we did not felt the need to make more video games. But what we wanted to do actually is test these video games on quality. So we tested 95 of them. And the first criteria we actually had is that the games need to be fun. If they are not fun, you're not playing them. So they need to be fun so you can keep the people playing the game, and then the concepts and the learning will get there if you're just playing the game for fun. Another requirement which we tested on was the effectiveness. How good are the quantum concepts transferred to the player? And also the quantum concepts, like how good are these explained? Let's say you have a power-up called tunneling, but in the game you are at 2 places at the same time. That is a bad example because tunneling does not mean being at 2 places at the same time. You should call that superposition. We also looked at the target audience. For example, if you have a really complex game, you shouldn't throw that at 8-year-olds. And also the background knowledge, which is kind of the same as target audience. If you want to play this game, what kind of background knowledge do you need to have? And this can be quantum related, but this can also be game related. As an example, I will explain soon. Quantum chess is one of the games we use. And for that, you need to understand the chess rules. So that's background knowledge you should have before you play this game. We had a lot of more criteria, but these are the main one we focused on. So here's a little snippet of our giant Excel sheet that we made, testing all the games with all the criteria and sorting them in quality. Currently, we have 18 games, which include VR games, board games, laptop games, browser games, even some tablet games, which really passed our criteria. As you can see in the green, it's not a lot of games, but we know these games are good, and we only want to use the good games. So if you're interested actually in these games, I will give a few examples. So you can take notes if you want to have some quantum games yourself. So one example I just said is quantum chess. On the left here, you can see the bishop. it wants to move to the top left. And to do that with normal chess, you would just move it. But with quantum chess, you actually have a quantum move. And this quantum move means that this bishop can be at 2 places at the same time. But the catch is that on each place, you have a 50% chance that your piece is there. So if you get taken on that spot, the game will observe if your piece is there or not. And then it will collapse the other piece because you will measure it, and therefore you are certain that it is there or not. So this really gives an extra dimension to the chess game. And when you play a couple of rounds against a player which also make quantum moves, your game can look a little bit something like this, which might look intimidating, but it's actually really fun, and it gets really confusing, and that's also what makes it fun. Another game, more friendly game if you have no prior knowledge, is Poseidon Delta. Poseidon Delta is a game which you can play for free on the web browser. You can play it single player or multiplayer locally on one laptop. And the catch with this game actually is that you have a wire over here. And all these blue dots is actually one electron, but it is in superposition, and you're not sure where it is. So you need to pull the lever to make a measurement, as you can see over there. And then you know where the electron is. And what you want to do is you want to take the enemy robot, put it on the surface, and then measure the electrons, hoping that you will measure it where the robot is standing. But this game also accepts from this level. These levels are like level 1, 2, 3. But if you go to level like 13 and 14, you can actually get quite an increase in difficulty and understanding in quantum concepts. As over here, you actually have a lamp on the left, and you can control that with different wave lengths and energy levels, because you need to bridge the gap of the energy level, because that is the shield the robot now has. If you bridge this gap, you actually shine a light on the electron, and you change the graph. And if you look at it from a quantum perspective, you actually change the probability density function of the graph, which is also a parallel to a particle in a box, because now you've got like the 2 peaks instead of 1 when you go higher in your energy level. So this is something you can actually really in-depth talk about with the players. The last one I want to show you here is Quantum VR. This is a game you can find on the Steam launcher. It is actually free. And in this game, you can program your qubits. So on the left, you actually have a H gate and an X gate. And you can also see that there's a block sphere behind it. So by picking up these gates and programming them in different orders, the block sphere actually changes. And therefore, you can visually see what the impact is of a quantum gate on a qubit. What we noticed from this game is if you play it in VR, we would say that you need to have at least like people playing it from 10 years or older, because in VR, you first need to understand the VR itself, and then you need to understand the controls and how you actually can play the game, which is like multiple levels of cognitivity, which is sometimes really difficult with the lower age. But now, if you have all these games, you want to get them to the people. And for that, we invented something called the Quantum Game Room. And a quantum game room is an area or a space or just a giant open place. And there you can set up your laptops, sometimes in VR if you got the room for it. and also the board games, meaning that the quantum game room itself is really flexible. And also because you want to have an open space, it is really easy to access for visitors to play and join the games. As you can see on the bottom left picture, for example, we were in the middle of a hallway where people could just walk by. And there, the children and the parents themselves chose to play the games, and out of their own curiosity, are looking what these games hold in them. And then they are way more motivated to actually sit through the game and understand how it works than versus if you actually force them to play the games. As I said before, you have public dependency. So if you go to a high school, you might not want to bring quantum VR with you. That might be a little bit complex. But if you go to like an elder or an older audience, Psi Delta might not be the game that connects with the people, as it is more childish like. So where can you put this quantum game room? So how do you actually get the games to the people? You can do that by going to high schools. And here I have a few beautiful pictures with children actually inside a quantum game room in their school, and people from education walking around to guide them. So at a high school, you can take over, or you can ask and plan with the school that you take one lesson hour. And in this lesson hour, we quickly give a presentation because we are guests, we are new, so you want to introduce yourself to the children. And after that, they can all play the games. They can walk around, they can ask questions, they can play together or alone. Everything is okay. Just let your curiosity about different games go. And if you get stuck, we walk around for the guidance. Once the hour is done, we actually use something we call exit cards, which is a card that have questions on them, like which game did you like the most, which game did you like the least, which concept did you came across, can you explain these concepts to us, and questions like that. So we can actually put them in an Excel sheet and see which games and what concepts actually really resonate with what level of education level for the high schools. So this is really insightful for going to high schools. Another example where you can put a quantum game room is actually at companies. So, for example, at IBM, they had a full day of quantum cryptography lectures to guests, which were from the banking environment. And actually to break off the lectures, we actually put down a quantum game room for the guests to show them that quantum can actually be really fun and interactive instead of just numbers and algorithms. We did this together with we did the IBM event together with Capgemini. And we also did some events for we did an event for the Dutch Ministry of Defense. Actually, they had a whole day about quantum and quantum initiatives, and we were there also to show off the quantum game room. Also, we work pretty closely with the Centrum for Quantum and Society, which we done a few events for, as you can see on the two right pictures, as they have sometimes national and international students and days also about quantum, and therefore we really connect with them on this aspect. There are more companies, but I will not list them all, so I can continue to talk. Some quick stats from our quantum game room, but you can make your own, of course. We currently did 33 events, and therefore we directly contacted around 4,000 visitors with quantum games, meaning that we have opened the eyes for at least 4,000 people about how quantum can be fun, interactive, and that you can look at it from another way. Yeah, so that's something that at education we are actually really proud of. So if we go back to the goal from this talk, how do you actually inspire the next generation with quantum video games? The first thing you want to have, so this is like our recipe book. The first thing you want to have is high quality video games. And you really want to have fun video games. If you're not having fun video games, nobody is going to play them. Because you cannot force yourself through a video game if you not enjoy it. So fun video games is a must. After that, you want, of course, that the quantum concepts in these video games are good. As I said, if you call being at two places at the same time tunneling, that's just incorrect. And you want to have correct terms, as these might be the first time that actually visitors or children or high schoolers come in contact with quantum. So you want to make a good basis. And lastly, the games that you use, they do not, you do not want them to have any bugs. Because if you have bugs, you might just quit the game. It might just lag out and you get stuck on a level, or you just cannot continue. And therefore, the motivation also just is completely gone. So high quality games is a must. Secondly, you want to have guides who understand the games and the concepts. Because playing a video game is nice, but if you get stuck or you find a concept that you don't understand, the easy path is actually to quit the game, ask for answers in the game, or sometimes even skip the level, which defeats the whole purpose of the quantum game. But if you have people walking around which know the answer to them, or at least know the concepts and therefore can hint or guide you through the next step, this really motivates the player to continue through with the game. And that's also really important. So have people available to help the visitors play the game in case they get stuck or they want to know more about quantum. And the last thing is to know your audience. So as I said before, you can play quantum chess with an 8-year-old, but he might not learn a lot from them. Maybe the chess rules, but that's not what we are here for. But if you give him psi and delta, he might actually understand that sometimes it is not certain where something is and you need to look for it, like observe. And that's already a term that then will be associated in the mind of the player. So you need to know your audience. You need to know which game you want to bring to this audience, and therefore make a good connection with the video games and the people who play it. So if we make a recipe book and you want to inspire your own people or visitors with quantum video games, you should have high quality video games. You should have guides there who understand the games and the quantum concept, and you really should know your audience. So that's the main takeaway from this talk. Yes, that is the talk. I want to thank Taha again for inviting me to talk here. If you want to contact us or have a question about the games or how we do it, we're really open to collab with everybody, because we understand that the quantum ecosystem needs to be open and collaborative instead of all building something new. So you can contact us with the QR code on the left. And of course, you can follow us on LinkedIn on the right, where we post, of course, pictures and our events update. And if you have other questions, you can also just email us at the email below. Thank you.
Yeah, thanks very much, Sjoerd, for this nice presentation and all of this wonderful work. I mean, everyone is now becoming excited to learn quantum finally. Yeah, like nothing will beat having video games to teach quantum. So it's a very nice effort. So let's now have the questions. Okay. Question by Ahmed Selim. It's nice. He says it's a nice idea. Is it a startup or a community effort?
Yeah, so I talked a lot. I will pass this question to my colleague. So Baste, you take the floor so I can drink a little bit.
Yeah, of course. Yeah. So everyone, I'm Baste. I'm chairman of Education, so colleague of Sjoerd.
Hey, Baste.
And right now we are a student team, and it's basically a community effort. So we get funding by the universities and by the University of Applied Science, so Fontes and the TUE, to get this started. Our goal is to get enough private income from companies themselves so we can basically fund our school visits by the companies. So when we go to like an IBM or a Ministry of Defense, we ask for a contribution from them, and with that contribution we can pay ourselves to go to more high schools. So for the high schools itself, right now it's free, and we have the companies basically pay for it. And to start us up, we get funding by universities, and we hope that we can make it self-sufficient. But we're right now in the starting up phase.
Nice. Yeah, thanks very much, Basten, for your answer. There is also another question from Selim. Are these online games available for children for free, or are these subscription-based? Selim wanted to use it to develop children and the teenagers' skills in artificial intelligence through quantum.
Yeah, so Quantum Chess itself, you need to pay for that. That's a paid game on the Steam launcher. But actually most of these games are free. Yeah, so you can play them on your own if you want to. You can find them online. You can contact us. We can send you some links if that's something you're interested in.
Yeah, question from Mohammed Amin Muradi. Also, are you able to take your game rooms overseas? Can you travel with your game rooms?
Yes, currently we abuse my car. We put all the laptops, all the VR stuff, all the banners, flyers, everything, merch, you call it. We prop it in my car. And then we just drive to a place where we're asked or where we have a meeting. So we've been to Delft, Arnhem, Utrecht, Eindhoven, like all over the Netherlands. So taking this overseas would not be a problem.
Okay, that's great to hear also as well. So maybe with the help of Mohammed, we can get a caravan or something, and then we go to try quantum games somewhere.
Sure.
Somewhere. Okay, that's great. Okay, is there more any questions? Okay, William has a suggestion. Yeah, please, Jan.
Good evening, good afternoon.
Jan.
Thanks a lot, by the way, for all the speakers. Very, very interesting subjects. But here I have a question for the last speaker, Sjoerd and Basten. Are you focusing with games to make people play games, or do you want to achieve something beyond the game?
Now go for it, Baste.
Well, for us, the video games are a tool. So they're a tool to get people exposed to quantum mechanics. And from my own experience, when I started doing quantum mechanics, I liked it a lot. And then I got more interested and saw the mathematics, and I immediately quit quantum. I have been quoted saying, I will never work with quantum or subsidy money, and now I'm working with quantum and subsidy money. But that's because of those video games. And we also have board games. And it's for us a tool to get people more against the quantum mechanics, and also to learn from the quantum mechanics. I didn't know what an Hadamard gate was when we started this project. I basically learned how quantum programming works through those video games. So the video games are not the goal; they're the tool for.
Okay, so but then you must be selective in the audience. I mean, it's great to make very young people play games, but if you want to give them some understanding of Hadamard gate of something else, a controlled NOT gate or whatever, yeah, then they should be interested in mathematics and in computer science, probably, and in physics, probably.
That doesn't really have to be the case, because that's something that was also a really eye-opener when I did my internship at Contraire. I think 25% were quantum engineers. The rest were mechatronics, programmers, designers, mechanics. So you don't have to push them only through a quantum education, but you can now lay the basis for them to not be scared of quantum if they come across it, or that they would see the quantum ecosystem as a viable option instead of something I'm not done for that, so I will avoid it.
I'm very content with your. I'm very happy with your answer. Yeah, because I do think that it is important that people start to understand a kind of other way of calculus, yeah, and which is a bit unnatural, yeah, and so I like what you're doing very much, yeah, so what you are saying is that you can deploy it at several levels of ages, yeah.
Yes.
And that's also very good to hear. Yeah. All right. Thanks for
Thank you.
the answers.
Thank you.
Yeah, thanks, Jan. Thanks, Boston and Short, for the answers. There is also a question from Dr. Murad. Are these games that are specifically based on entanglement? Do you depend on entanglement all the time, or how these games are designed?
I'm thinking. I can think for you mean like one game fully about entanglement, or a game with entanglement as one of a power-up, because there are a few games which have entanglement as a power-up or a showcase how you can use it.
Just mention some examples.
How I see in quantum chess, for example, you can actually, let's say you have your bishop at a 50%, and you go through it with a tower. The tower itself will be entangled to the bishop, because if the bishop is not there, it can't go through it. But if it is there, it can't. So they are entangled with each other, depending if they are there or not. And then the whole system will like collapse if you observe one of them, because then you know for certain where the pieces are. So that's one example of entanglement.
Mm-hmm.
Yeah, quantum tic-tac-toe, I see it in the chat. Yes, that's also a very good example of entanglement. Thank you.
And we are going to use it because we are going to now go also on behalf of TLC Amsterdam to participate in a hackathon called the Y 2025. Maybe you are going to go there as well. Maybe you can meet. So that's like a big camping like below Alkmaar. So they are going to use a tic-tac-toe tournament there as well. So yes, that's going to be interesting. So another question that pops up from the discussions. How do you envision, for example, commercializing this idea in the future? Yeah? How do you see it, for example, in a year or two from now?
You want to go for this?
Yeah, so that's what we've been working for the past 2 years. And the first starts was, of course, getting the quantum game room up and running, getting the enough people to actually host all of them. And now we're starting to slowly go into the commercialization. So we're actually contacting companies and basically offering a game room for usually like an hour, hour and a half. We have done events of days, for example, for a RoboCup. And I think that is our way towards commercialization, because if we can help the students become engaged in quantum mechanics, then for the companies in like 5-10 years, they will have graduates that are knowledgeable in quantum, that know what quantum is, that might decide to study physics because they like quantum. That's for our way towards commercialization is getting those companies engaged and having them believe in that we can actually add to this workforce.
Okay, that's really great to hear. So very nice efforts and very nice work. Perhaps let's see if Saskia would like to say something.
About what?
Yeah, if you like to comment on the effort. I mean, they are mentioning your names.
So we are very proud of our students. Yeah, Boston and short compliments.
Thanks. Yeah, that's really great to hear. So yeah, thanks very much. Yeah, Jan, please go ahead.
Yeah, I have an intriguing question, I think. My assumption is that for all these games, you use either simulated data or you use a little simulation kernel in the game, yeah? So you don't use a real quantum computer in the background.
That's true. Actually, what is really nice is that we are currently exploring one of the games which actually uses the quantum computer that is based at the DOE. So how far in development that is not from our side to talk about, but we are in contact to actually get one of the games actually backed up by calculations and interaction with a real quantum computer.
Yeah.
And the rest is indeed simulations, as you said.
That is a very good development, and I hope you can.
And we also hope that it's a good game.
Because today, I think many projects stick in the simulation, in the emulation phase, yeah? While real quantum computers are available, and in the end, we want to deploy real applications on real quantum computers for hopefully real production in a couple of years. And but very good answer. Thank you very much.
Good question.
And good luck.
To add to this, one of the challenges with actually using real quantum computers is latency. So if you want to keep a game fun, like we found a few quantum games that used to use like an API from IBM, but now they don't work anymore because the API.
So I understand the problem. Yeah.
There is a balance basically.
Yeah, no, I really understand your the issue with latency or the changes in the programming environment. It's getting better, but I understand the principal problem. Yeah, good. All right, thanks.
Okay, so is there any more questions? Okay, so if not, I would like to thank our speakers. Yeah, Saskia has already mentioned also a report. Okay, please. Yeah, please read it. Thanks very much, Saskia, for the share. So I would like to thank, let me just share. Okay, this is the bios. Okay, I would like to thank our speakers, and I would like to thank also in particular also our last speakers, Sjoerd and Boston, for the nice presentation. I would like to thank all the speakers, starting from the beginning, from Dr. Ahmed Younes, Dr. Murad Telmini, Alan Shansay, Dr. Mohammed Amin Muradi, and Sjoerd and Boston for all of this nice work. I'd like to thank the audience for all of the nice discussions and nice questions, and thanks very much for also Saskia for carrying on the discussions at the end with Jan to stream it up. Thanks very much, and we are looking forward to hosting you again in the future. I think the quantum has a lot of we learn from, and also along to collaborate on and discuss, and all the time new ideas come from discussions. So thanks very much, and hopefully we meet one another again in the future series. So this series is held every month, and I think in this time of the evening, if we are all interested in quantum and up and running and discussing quantum, yeah, this is a good thing indeed.
Yeah. Also, thank you for organizing it and hosting it.
Yeah, thanks very much. Thanks a lot.
Thank you, Taha.
Yeah, thanks a lot, Murat. Yeah, thanks very much, and I wish you a nice evening. Yeah, thanks. That's a nice day.
Same.
Yeah.
Bye-bye.
Bye-bye.
Thank you, everyone.
Thanks.